So for this geometric distribution example, and this is out of your book, example 317, we've got an offshore oil platform. It's been designed to be 8 meters above mean sea level. Of course, we know sea level goes up and down, but got to peg it somewhere. So 8 meters above mean sea level. Based on buoy data, so where does this data come from? Buoys are out there in the ocean or the Gulf, and they can record wave heights over time. So say we've got like 30 years of buoy data, and we know that looking back at the maximum wave height in a given year, that this particular wave height of 8 meters corresponds to about a 5% probability of being equaled or exceeded in a given year. So annual exceedance probability. We're going to be using that term a lot in hydrology. So first we'll calculate the return period for this wave, or recurrence interval. So return period is equal to recurrence interval. We define it as T bar. That's 1 over P. So that's our 20-year flood, right? Or 20-year wave. And maybe it's not the end of the world if a wave hits, exceeds the height of the platform, but it would shut things down for a day or two. So it's kind of like an intermediate type of risk analysis there. Okay, so let's calculate the probability that this design wave calculate the probability that will be exceeded within 20 years. And so this would be the probability that the height is greater than 8 meters in 20 years. And maybe that's the operational life of a platform is 20 years before they have to decommission it or something like that. Greater than is hard. So we're going to make that as 1 minus the probability that it's less than. And we can then write that as 1 minus that we basically don't get this recurrence interval, it doesn't happen. So this is going to be 1 minus P to the n. So this ends up equaling, we'll just do 1 minus 0.36. So we get about 36% chance that that wave will be equal or exceeded in 20 years. Now we can do another one that's a little more involved. Let's calculate the probability that a wave height that exceeds 8 meters will occur after the 3rd year. We'll call it design wave. So this specifically gets at the geometric distribution. This is the risk equation from before, and this is the geometric distribution. So this is the probability that, we'll say t is greater than 3. I'm going to do n. I like n better because we've been using n for the geometric distribution. So n is greater than 3, which is going to be equal to 1 minus the probability that n is less than or equal to 3. And this is our CDF. And because it's a discrete distribution, there's no way to like do some cool integral here. So we just have to add things up. And so the geometric distribution is p times 1 minus p to the n minus 1. And so we're just going to have to sum that up for n little n to big N. So we can write that out. We'll do 1 minus, and then we get 0.05 times 0.95. So the 1 minus 1 plus 0.05 times 0.95 to the 2 minus 1 plus 0.05 times 0.95 to the 3 minus 1. So if we do all that math, then we end up with 0.857, or about 86%. So 86% chance that it's equal or exceeded after the third year. And maybe that's a question related to building a thing out, or what kind of safety provisions do we need to have, that sort of thing. Great. So that is what we'll do for today.